we invite Mr. Kapageridis to give the next presentation again with the title Application of Machine Learning to Resource Modeling of a Marble Quarry with DomainMCF. Please, Mr. Kapageridis.
So it's me again. This is some work that has been going on for some time. We have been involved in resource estimation for Iktinos Hellas in Drama for a few years now. And we have tried something different in the last few months. Now, a few words, first of all, about our case study and the particular deposit in Volakas. Iktinos Hellas is one of the major companies active in marble quarrying in northeast Greece. Has a number of marble quarries, mostly located in the Eastern Macedonia and Thrace area. The Volakas quarry is located northwest of the city of Dramas, as we will see in a moment. And the mountain Volakas hosts a number of marble quarries. Practically everyone who is someone in the marble industry has a quarry in Volakas. In the last few years, a lot of these companies have turned into underground quarrying as well. And Iktinos has started a few years back to do that as well. So this is the location, as you see with a little square at the top of this image, the location of Mount Volakas, and you can see with the white pixels in the detail photo where the quarries are. There's a lot of them, they are neighboring each other, and they are struggling for space. So marble deposits are quite interesting when it comes to modeling them, because all the information is mostly qualitative and not quantitative. We don't have numbers, we don't have assays to play with. It's just categories. So it's much more difficult to find a system to estimate resources. Now, in the case of the Volakas marble, and Iktinos, of course, because not every company that has quarries in Volakas actually follows the system or any system. The following parameters are identified by the company itself and used to characterize the marble features that are significant to its quality classification. All marble companies sell marble of different qualities, like A, B, C, and so on, or they might have a different system. Each of these qualities is based on a number of parameters that take different values. So lithology plays a role, first of all. We talk about mostly dolomitic marble or calcite. Iktinos identifies the type of marble, in this case as being flower-like or diagonal vein features. You'll see in a moment in some pictures what all this means. There are other types as well, but these two are the main types being found in this particular deposit. The background parameter, which is related to the presence of visible defects like glass or some decolorization, and tectonic features of different orientation. We'll go through them very quickly, one by one. So you see here two types of marble from this deposit. On the left, we have the flower-like features. Okay, they're not flowers, but they, you can use your imagination to get there. And you also have diagonal features, which are more linear in the mass of the marble. Okay, there are others as well. So the samples that come from drill holes, and Iktinos does a lot of drilling, unlike other marble-producing companies. Iktinos is very good in that effect. They take the core and they try to characterize it as to these parameters. So we get a database with different categories for each sample, and then of course the question is, what do we do with it? We have background as well. You can see here 4 different background types, okay, from very clear with no presence of calcite crystals and stains to very dark background with veins or flowers of varying thickness with dense calcite crystals, which is glass basically, and stains. So we have these different categories as to the background parameter. All these parameters are visual, so they are kind of interlinked. They're not very, separate to each other, but Ectinus is trying to have a system. And then, of course, tectonism, all the discontinuities we find in the marble mass. And in this particular deposit, they measure it according to groups of, or the density of discontinuities in 4 different groups, depending on the dip direction and dip. So 0 means there were none of this particular group. 1 means there's at least 1, 2, and 3, and more. So we have all this information. It's all categorical. Even this is categorical, even though it looks like numbers. It's not something we can just interpolate and say in this block we'll have 2.5 discontinuities or something like that. Okay, it's all very, it's just a classification basically. So we have all these parameters, and we figured out years ago a conventional method to classify the blocks and produce some volumes and some resources. Now I'm going to use the word resources in a very light fashion and not with a capital R as I did in my previous presentation, because I don't feel comfortable talking about mineral resources and reserves when it comes to this kind of estimation. Okay? So R with a lowercase r in resources. Okay, now because it's all categorical, conventional estimation methods would include things like indicator kriging, or the system we developed, well, developed is a big word, but anyway, we set up here using indicator values and some inverse distance weighting interpolation. Okay, and that's to do with, I'm sorry to say, software limitations, but that's what it is. So Ectinus has been using a special version of Vulkan called Quarry Modeler since 2014 and has implemented this methodology. And in this methodology, we turn all of these parameters you saw before into indicators. So if a sample belongs to one of these categories, then a particular binary kind of variable for that, it turns to 1 or to 0 if it doesn't belong to that particular category. So we have, for example, 4 different tectonic variables, and we have 4 different values for them. That's 16 different variables or fields inside our database, okay? That can take a value of 0 or 1. And then we go and interpolate all those zeros and ones in 3D space in a block model, then combine all the results together, consolidate them to come back to our original quality, okay? And we have to do that, and we cannot work with the original qualities because all of them have a different orientation in space. They have a different anisotropy. So we have to use a different search ellipsoid when we're looking for samples when we do the interpolation. That's too much detail. Let's go forward. So we have a block model. The volume of the deposit is split into blocks. We estimate all this information in the blocks, and then we consolidate all the information using a block model script to derive the finite classifications and be able to calculate resources. Now, when this company that produces Vulkan introduced this new system called DomainMCF, we were quite excited to use it, and thankfully Maptec allowed us to use it through an early access program. This system is, well, it's called DomainMCF because it's supposed to be doing exactly that, to be used for domaining of a block model. Okay, and it is used to model the spatial distribution, in this case, of marble quality characterization parameters, and the resulting values were again combined using the same classification system. And this is a cloud processing service. DomainMCF is a cloud processing service. It requires a lot of computational power, nothing we could have access to in our personal computers. And anyone who was interested in this access program was given access to it for a few days to run some examples and then take the results and work them out. It is based on artificial neural networks to model the spatial distribution of discrete domain values from a set of samples. So that looked like ideal for the case of marble, where we're dealing with discrete values anyway. And we thought that we could build up a case study out of this. So how does the neural network work in this case? Well, it's very simple because it has only 3 inputs. The x, y, z coordinates, When it's being developed, these are the coordinates of the samples. When it's being applied, these will be the centroid coordinates of the blocks. So you can train it on your on the data set you have from your drill holes, and then apply it throughout your block model. Okay, the output with D is the domain. In this case, would be each of the 7 different parameters we have for type, background, lithology, and so on. And you can also provide the grade as an output. Now, this doesn't make any sense in this case because we don't have grades, but in cases where the deposit, the domains we identify are also grade-driven, like would be for Larco, for example. In the laterite deposits, we have domains that relate also are defined by grade in some cases. This could be also used. At this stage, grade is used to drive this development and not actually to produce grade estimates, okay? Because it's a much more difficult thing to do. And in fact, as you can understand, this thing just maps XYZ coordinates to some discrete value in the domain and some numerical value in the grade. To think that a single network can map an entire deposit, regardless of how complex it is, just using this kind of simple mapping, is not necessarily, a very good thing to think about, okay? It can be done, but it's not always like this, because not all deposits are the same, okay? Of course, the more complex a deposit, the more samples you need. The more samples you need, the more hidden layers, processing elements you will need, and more time to process. Okay. Now, of course, ANN development is data-driven, and that's largely dependent on the quantity of the and quality of the data. The more data you have, the better model you will build, and the more reliable the results will be. In the case of domain modeling, obviously more samples are required to produce a representative model in a more geologically complex scenario. And as I said, it would require a more complex architecture as well. Now, this thing can also produce results even outside the sampling area. But as any other system, this is like some kind of form of extrapolation, and the results should be treated with care. Okay, it's not just because it says you get this value there, you should think about where was your last drill hole, okay? How far you are from your sampling area, just as in any other case. The data used in this study included 95 drill holes in a quarry, in a marble quarry. You cannot find a lot of marble quarries in Greece, particularly with 95 drill holes, okay? In other cases, in other kinds of deposits, you might say, oh, 95, I cannot work with 95, I need 200, I need a few thousand. But for marble, it's quite astonishing that they do all this sampling and quarry face analysis as well. And that gave us 3,570 1-meter samples to work with. Most of the drill holes are vertical. You cannot see them in this plan view, but they also have some horizontal ones that intersect areas of interest for underground quarrying. The sampling obviously is quite irregular, unlike what we would ideally have, and that brings certain issues to our modeling procedure, but it is what it is, and we have to deal with it. We have 2 minutes. Okay. So DomainMCF, this is part of the interface. Very simple. You open your data. We have, oh, okay, just something happened there. We have all the different columns from the CSV files which we produce from the database. We choose the 3 columns which correspond to the XYZ and the fields that correspond to the required domain output. And of course, we also define the block model analysis and all that. And then we run it. We submit the project to the cloud service. It gets queued, then it runs, and then you download the results, and then you can open the block model as any other block model in the software and view it, compare it with your drills, compare it with your other systems you've been using before. These are just plan sections through the estimates. You can see the different category, the different domains for each of the 7 different parameters. The last 2 tectonic ones, they don't present much interest in general. They're very uniform, but there was quite a lot of variations on the other parameters, and these were combined to produce the final classifications and compare them with the original inverse distance-based method. Now, you shouldn't get confused about the fact that DomainMCF has estimated the entire area. It can do that, whereas in inverse distance, in the other method, because we're using a search ellipsoid and a limit for the number of samples, we just limit the area of application. So you can tell straight away, regardless of all this brown area around, that the DomainMCF system has produced more uniform distribution of estimates, okay? That can be good, that can be bad in some cases, but generally speaking, it makes more sense to see these results, particularly for marble qualities, okay? And other than that, we see a lot of similarities between them. I would say it's very early stages, of course. This was a very early study, and we're not trying to convince everybody that, you know, this is it, and we'll switch to that forever. But it's very promising. It produced very sensible results, okay? And we can see that even in section view. This is a typical section between the standard method used right now and the results produced by DomainMCF. And again, we see a very reasonable distribution of marble qualities inside the area of interest. Of course, areas far away from the sampling area are not to be trusted or be compared between the 2 different methods. Okay. Now, in addition to that, and I'll try to rush through this, DomainMCF produces also a confidence level kind of value that can give us a measure of confidence of the system to the results that it produces. To be honest, I'm not sure yet how this is actually calculated, and this obviously takes me back to my previous presentation, but it is something we can understand how how it get calculated during the development of the neural network. But then, of course, you must know something about neural network development to understand this kind of confidence value. And you can see here the kind of values we receive from the system when it tries to estimate one of each of these different parameters. Okay. I'll get back to that if you have any questions later. Now, in conclusion, okay, it's very quick to produce those marble classifications. Each of these runs, there were 7 runs, took 2 minutes. So the whole study, processing-wise, took 15 minutes to complete. Okay? It produces more uniform marble classifications. Okay, that can be an advantage or not. It requires no structural analysis of the categorical parameters. We don't need to do variography or anything else, obviously, because we're dealing with the machine learning system. The sampling pattern has no effect on the difficulty of the process. Anybody involved in trying to do variography with this kind of irregular sampling, it's very difficult, okay, because they're not, it's very difficult to find pairs of samples to calculate the variogram. And of course, because it's a standard software from a mining company, it can communicate with the rest of the mine planning package very easy. Now, for future, it would be great if we can use anisotropy in predicting those parameters, because right now the system works on its own. We have no control of how it produces the estimates it produces. It would be great if we can say, okay, use this orientation for type and that orientation for background and so on. Okay. It would be good to have, it's important to have better understanding of confidence level values produced, how are they calculated, how they can be interpreted, okay, and if we can associate them with resource categories. And of course, more testing needs to be done to investigate the influence of the grade field, not in this case, of course, because we don't have a grade field, but for other cases. Okay, so that's it. Thank you very much for your attention.
Thank you, Mr. Kapageridis, dear professor. Is there any question from the audience? No? I have one too, but there is here. Okay. From Mr. Vasilios Yatros.
Okay.
First of all, thanks for this excellent presentation. I'm a graduate geologist who recently has an interest in machine learning and neural networks. In this case study, what was the block cell size of this model against the overall volume of the mine? Also, the efficacy of the modeling is homogeneous in the whole area, or there is a spatial distribution?
Okay. First question.
If you
is-
need more time to answer the question,
No, no, I can answer
you can-
directly.
okay.
No problem. The block size was, I think, 6 by 3 by 2, and it relates to the size, well, the bench height in the quarries, and also the size of the slices produced by during the quarrying operation. Now, the second question was about the efficiency of
The efficacy of the modeling is homogeneous in the whole area, or there's a spatial distribution?
No, there is, I don't know if it wasn't clear from the section and the 3D model colors. There was a special distribution that was related to and verified with the drill holes. So we had a good match between what we saw on the drill holes and what the system produced. Okay, I hope that answers the question.
okay, sorry, very quickly question. You have the classification, you make the classification according the aesthetic characteristic and
Yes.
the tectonic of the marble.
Yeah.
It's not better to insert the physico-mechanical tests of the marble?
I'm not in a position to answer that because this is the system that the company has been using even before. This is how they classify their products. I don't know if there's any correlation between these properties and the actual classification. It would have, these are, of course, parameters we use when we do like the study of the stability of the
Yeah.
underground quarry and so on. But when it comes to marble quality, I think it's all visual. It's not.
Because of the underground coring now, I think the...
Yes, it's very important for that
it's very
and for
important.
designing the.
Okay,
lumen
thank
pillar.
you.